Okay, this is the last question that I want to discuss today. So I will quickly go through this question because it's very simple, just evaluating limits. And since we have time, then I will talk about infinite limits, limits involving infinity, and also asymptotes. Okay, so let's settle these two quickly. So first of all, you have a look at it. You know that you have to do multiply by conjugate. You need to rationalize. Why I don't want to do L'Hopital's? Because you have a square root. If you do L'Hopital's, I don't want to see a lot of stacking fraction. Okay, so that's why I just do, it's easier to do rationalize in this case. Sorry. Okay, x approach -2, x plus 3 minus 1, x plus 2. Okay, multiply by conjugates, plus 1, x plus 1, x plus 3 plus 1. Okay, and on top you can just make use of the difference of square formula, a square minus b square. And for the bottom, I told you, don't expand first. See what you can cancel first. And in this case, you see it's very obvious. You can cancel out something with something on top, right? Just leave it like this. And one more step, then you should be able to see x plus 2, x plus 3 plus 1. Okay, so this and that can cancel. It should be 1 over square root x plus 3 plus 1. Can you sub in a -2 now? Yes. So it is 1 over square root -2 plus 3. Sorry. -2 plus 3 plus 1, which is actually 1 over 2. That's it. Very simple. Then for question B is even more easy. Just that whether you can see or not. Okay, so this is actually very simple. Don't be scared by all kind of scary power there. I think I'll get rid of this. Okay, let me get rid of this because I need the space and I need the question. Okay, sorry. I might just erase the whole thing. Okay, so if you have a look at it, on top is actually also difference of square, isn't it? A square minus b square equals to a plus b, a minus b. What about bottom? It's actually your a minus b. Okay, so just write down all the steps. You have to do the work. Okay, so e x minus 1, x plus 1 minus 1, e x minus 1, x plus 1 plus 1 over e x minus 1, x plus 1 minus 1. So this and that can cancel. Can you sub in the 1 now? Yes, you can. You will not get anything crazy, alright? So now it will just be e to the 0 plus 1, which is 1 plus 1, which is equals to 2. Finish. Okay, yeah, so that's all for the STPM past year question. And now I want to talk about infinite limits. Okay, let me get to a blank page. Right? So limits involving infinity. Okay, limits involving infinity. And actually there are two types of limits involving infinity that I want to talk about. Involving infinity. Okay? You know that for limits you have C and L, right? Limit when x approach C, not necessarily x of fx is equals to L. You have this C and L. So one case is your C equals to infinity, another case is L equals to infinity. It's actually positive infinity or negative infinity. Both are actually the same concept. Okay, so let's look at the first case first, which is your C equals to positive or negative infinity, which is limits to infinity. Okay, so if you have this one, let's go through the concept first. X approach infinity of fx is equals to L. Alright, so again we come back to the definition, okay, the epsilon delta definition, but in this case we only have epsilon, because we are dealing with what? We're actually dealing with your fx, not your x. Okay, so for every epsilon, which is a very small positive number greater than 0, there exists a number. Okay, maybe this time I don't use delta because it's not delta. Maybe I choose m, alright, m, such that the absolute value of fx minus L is smaller than epsilon. Is smaller than epsilon whenever your x is greater than m. You see a difference between this and just now the one-sided limits, and actually the difference between this and epsilon delta definition limits both sides, right? Okay, so x greater than m means what? Means your m is here, just a random number m, and your x is everywhere here. Okay, your x is here. So from the statement itself, from the theorem itself, you can see that when x is here, when x is anything greater than m, the value of fx, what happened to the value of fx? It should be very, very close to L, isn't it? Okay, so this will be L minus epsilon, L plus epsilon. So meaning when after x is greater than m, your fx should be somewhere here already. Even though it is maybe very, very big from just now, now becomes it will converge, it will approach this line L. Okay, so this means that you see, your x become very, very big. X approach infinity. Of fx will converge to one particular number, which is L. One more time. When your x becomes bigger and bigger, which means x approach infinity, your fx, you see your fx, will be bounded between L plus delta, L plus epsilon and L minus epsilon, which means the difference between your fx and the particular L, whether it is more than or less than, doesn't matter because we put a modulus, is always smaller than epsilon. Okay, so this is the concept of limits to infinity. Then what about negative infinity? It's actually the same. Just that you replace this one, negative infinity. This one don't touch, don't touch, don't touch. Just that this one change. X smaller than m. Okay, means this is the other side. Okay, m is here, now your x is here. Okay, this is your x. Okay, and actually it's a same concept. Okay, your L and then your epsilon. Okay, so actually they are the same. So let's look at one very simple example, which is, I will just tag, this one is, I think is easy. Show that the limit when x approach infinity or 1 over x is equals to 0. Very easy, right? Very easy, right? Actually, you always use this when you do, what's that? When you're trying to compute infinite limits, right? You always make it into 1 over x or 1 over x squared. Then x approach infinity, and then you immediately set this equals to 0. This is how you always use, right? But now I want you to prove that. Okay, so you write down the proof. How you gonna prove that? I gave you a template just now, isn't it? Given, choose, suppose, check. I'm a little bit running out of space, but yeah, let's do this. Given, okay, now you are dealing with what? You are dealing with fx. So, still given epsilon greater than 0. Then choose, this time is not delta, because you don't see any delta in the theorem, right? So you need to choose your m. Choose m what? Such that x is this one greater than m. Suppose your x is greater than m. Then which one do you need to check? You need to check this one. And who is your f of x now? It is 1 over x minus, who is your L? Who is your L? 0. Okay, it is smaller than who? Epsilon. Very simple. And because now your x is at positive infinity, right? Means your x is very, 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 very big positive number. So where do you think that do the modulus sign still matter? No, it doesn't matter because your 1 over x will always be positive. Okay, so now I want to make this to look like this. How can I do that? I just take the reciprocal on both sides, right? So if we take a reciprocal, we need to change the sign, meaning your x is greater than 1 over epsilon. And now can you determine your m? This is just your m. M equals to 1 over epsilon. Hence, you have x greater than m. End of proof. Okay, so this is the limits involving infinity for when c equals to infinity. Okay, so from here, I want to talk about horizontal asymptote. Okay, let me get to a new page. Okay, so let me write out a theorem again. If your limit x approach infinity of fx equals to b, or the limit when x approach negative infinity equals to this number b, then y equals to b is a horizontal asymptote. Okay, horizontal asymptote of the graph of function fx. Okay, so this is a theorem. What does it mean? Actually, it's very easy to understand. Just that when your x, from just now you see, your x is like infinity, right? Going to infinity, this is your x. And then it will approach one value, in this case is b, right? So it is either positive or negative, doesn't matter. Okay, you want to from top, from bottom also can. Okay, doesn't matter. Okay, as long as the value when you take the limits to infinity it will converge to one value, this particular value b, then we say that y equals to b is a horizontal asymptote. Okay, let me clear one misconception that you always have. When we see the word asymptote, okay, in elementary level, in the function chapter, we always say that, oh, the graph cannot cross any asymptote, isn't it? Including the, the trigonometric function. When you have a tangent, you know that, oh, you have the asymptote at x equals to pi over 2, right? But the truth is, it is possible for a graph to cross horizontal asymptote. Okay, it is possible. And you will see a lot of them. Not a lot. You will see that kind of graph when you go to the graphing chapter, where you use the derivative to find the maximum, minima, inflection point, that one. Okay, so yeah, I will not talk about it here because now I want to focus on the concept of limits. I just want to talk about the asymptotes from the aspect of limits. Alright? Okay, so now let's move on to the second one, okay, which is your L equals to infinity. Okay, and this is what we call as infinite limits. Which means if you plug in the value, then you will get an infinity. Okay. So again, I will write down the theorem for you. The limit when x approach c, fx equals to infinity. Okay, so if we say this, then this is a little bit different. How should I phrase it? Okay, for every real number, for every real number Just now we use m, now I use n, right? Real number n. There exists. Just now we have epsilon. Now I will use, and now we have delta. Why? Because now we are dealing with the x. Okay? There exists a very small positive number. We call it delta greater than 0, such that your fx is greater than n whenever your x minus delta is in between 0 and delta. This is actually very easy to understand if you can understand the previous one. Okay, so if your your c is here, this is c plus delta, c minus delta from here and delta. Okay, remember this is no longer one-sided limits, yeah? We are dealing with two-sided limits. Okay, so it means your x can either approach from the left or from the right. Okay? But this time is different. Because we are only dealing with positive infinity. Actually for negative infinity is the same. I will show you later why. Okay, so if your n is here, based on the statement, you can see that when your x is within this interval, when your x is somewhere here, okay, then what happened to your y? Your fx should be greater than this n, isn't it? Okay, perhaps maybe I shouldn't use this color. Okay, I just use black color for now. Okay, so means your fx should be here. Okay, this is your fx. Okay, this is your fx. If you graph it, maybe something like this. Go to positive infinity. Okay, actually is, yeah, just 1 over. Okay, no. I don't give any function here. I just want to discuss the concept. See, and this n appears to be very big number, isn't it? When your x is equals to this number, see, it is positive infinity. Okay, so this is the idea of infinite limits. Then what about negative infinity? The same thing, your limit x approach c, fx equals to negative infinity. For every real number n, there exists a delta greater than 0, such that now your fx is smaller than n. Okay, it is actually here. Okay, now your n is here, going to negative infinity. Your fx is here. Okay, and whenever this one is still the same. Okay, so this is the theorem for infinite limits. And from that infinite limits, I will talk about vertical asymptotes. Okay, so again, the theorem, if the limit when x approach, maybe I don't want to use c anymore, maybe an a. Did I use a any? Just now I used b, right? A from the left, from the right, okay, is equals to positive or negative infinity, or the limit when x approach a from the left is positive or negative infinity. Okay, means it is like this. It's either this is your a, okay, from the right it's positive negative infinity, or like this, something like this. From the right or from the left, it is positive or negative, doesn't matter. Okay, if this happens, it happens to be if you approach that number, if any one-sided limit when x approaches that number a is infinity, then you have a vertical asymptote. Okay, then what is the equation of your vertical asymptote? It's this one, isn't it? So then x equals to a is a vertical asymptote for the graph of function fx. Very easy to understand, right? And because when we are in the function chapter, when we deal with range, domain, everything, right? We said that x cannot take that value because it will result in undefined positive infinity. And now you know that it is actually your vertical asymptote. Okay? So I don't think I will go into detail for this asymptotes. But since we are talking about asymptotes, then let me show you one more, which is the last one. What we call an oblique or what's that? Slant asymptote. Just now we have either is y equals to something or x equals to something, isn't it? One is horizontal, one is vertical. And now these slant asymptotes are actually like your linear equation. You can write it in terms of y equal to mx plus c. Okay, so means it is a linear equation line. A linear equation line. And your graph somehow cannot pass through it. Something like this. Something like this. Or something like this. Cannot pass through this slant asymptote. Some magic barrier there. Okay. So when will it happen? It happen when you have a rational function, okay, fx over gx, and your degree of fx is your degree of gx is 1 more than the degree of gx. Okay, so the degree of fx is one greater than, okay, gx plus 1. And in fact, your asymptotes not only can be slant or oblique, it can be quadratic, it can be cubic asymptotes, depending on the difference between the degree of numerator and degree of denominator. But in this case, I will only talk about the oblique or slant asymptotes. Why? Because the word oblique look very nice to me, and it's very, very nice to say that oblique. Okay, oblique asymptotes. Okay, so let me show you maybe one example. You see, the degree. Okay, so if you look at this one, the degree on top is 1 greater than the degree at the bottom. What comes to your mind? Improper fraction, improper rational function, isn't it? So let's say I give a very simple example. Fx equals to maybe x squared minus 3, 2x minus 4. Okay, you see the degree on top is 2. Degree at the bottom is 1. Degree of on top is 1 greater than the degree at the bottom. Improper fraction, improper function. What do? Long division, isn't it? Use long division. So let's go ahead and do long division and see what happens. Okay, plus 0x minus 3. Okay, then you have a 2x minus 4. Okay, so you have a half x. So that you have x squared minus 2x, 2x minus 3, then plus 1, 2x minus 4, you have a 1. Okay, so this will just be, let me write here, by your Remander's theorem, it will be 1 over 2x plus 1 plus 1 over 2x minus 4. Okay, by your Remander's theorem. And when you say this kind of thing, you ask yourself, because you want to find what, when we talk about asymptotes, it's always dealing with infinity. And the reason why I put it here, because why I discuss it now is because I want to show you the concept of limits here. Okay, so you ask yourself, what happens when x approach infinity of this function? So when your x get very, very, very large, you know that this one is definitely not going to converge. It's actually still infinity. It's still infinity. So it's actually pointless. It's actually pointless to say anything because it's still infinity. But what I want you to take note is, when x become very, very, very big, what happened to this one? This will be 0. Which means, who is the dominant term in this function? It's half x plus 1, isn't it? This is what we began, dominant term. So when x approach infinity, you can actually ignore this part. You can actually ignore 1 over 2x plus minus 4. So who is your oblique or slant asymptote? Is your, this one. This is your slant asymptote. Y equals to half x plus 1. Okay? Okay, you make a note of it. Make a note of it. Why is it a slant asymptote? You think about it. It is the dominant term, right? And I told you that you can actually ignore this one when your x get very, 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 very big. But does it mean that the entire term here doesn't exist? No, it still exists. So, you know that your graph will always have this very, 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 very small number. And this very, 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 very small number is the difference between this fx graph and this oblique asymptote equation. So it is an asymptote because it will become very, very, very close to that line. Okay, let me draw it out for you. Very hard for me to explain. Very abstract. Okay, this is your half x plus 1. This is your graph of y equals to this one. I don't know how it looks like that, but it should be something like this. You see? Very, very close to this line. But still didn't touch the line. Because what is in between here? What is in between here is actually this very, very small fella. 1 over 2x minus 4. They're still there, just that it is very small. And this is the oblique asymptote. The concept of oblique asymptote and the concept of limits. Why do we need limits to determine asymptote? Okay, so I hope I can give you some insight by talking about this oblique asymptote, because it is actually not so important in the syllabus. Mainly it's about, what's that? Vertical and horizontal asymptote and limits to infinity. Okay, but this to give you an insight to have a better understanding on the importance of limits when we talk about asymptotes, right? Yeah, so we are done with all the STPM past year question that I want to discuss. And actually, we are almost done with the chapter. I think I've covered all the important concepts, except for one thing that I didn't see in my this revision past year question, which is trigonometric limits. Okay, so I will talk about it in my next lesson. Okay.